I see now that 62 people are in the meeting right now. More people are coming. I suggest that without further ado, I can introduce Rod Robinson from MPL, also participating in the project of MetCCUS, who is going to talk to us about emissions, particularly CO2 emissions. So the floor is yours, Rod. If you want to start right now, or we just wait one more minute, as you prefer.
Okay, I'll just introduce myself while people are joining. So welcome back from lunch. I hope, according to Miguel's slide, that you all had a bottle of wine and a tub of olives. That'll certainly make you appreciate my talk more. So I'm Rod Robinson. I'm Principal Research Scientist in the Emissions Atmospheric Metrology Group at MPL. I head up our emissions work, and as Iris and Miguel said, I lead the Work Package 2 emissions work. So in this talk, and as Iris said in her introductory talk, within the emissions work, we've got three broad activities. We are looking at emissions from the capture process itself. We're looking at fugitive and diffuse emissions, and I will come back to that, from the infrastructure, particularly the above ground infrastructure, and we're looking at potential approaches that can detect emissions from the storage process. You'll see on there also I've identified the partners who are involved in this project. And this just highlights some of the areas across the CCUS process or value chain where we're looking at emissions. You'll note on there I did identify direct air capture as something we're not explicitly looking at. There are some interesting potential measurements as to whether you can see the depletion of CO2 in the atmosphere and what the atmospheric loading is, but it's not something we are directly looking at. Just to flip back to one of Miraz's questions in the opening session. But we are looking at the fugitive and diffuse emissions from the infrastructure. We're looking at potential ways to monitor emissions from offshore storage. And we're looking not only at CO2, but also other pollutant emissions from the capture process. What I'm going to do in this talk is not go through in detail everything that we're doing within the project, but just highlight some of the activities and some of the areas where we're developing some of the metrology support, and just touch on some of the work that we've done so far. I'm going to start looking at the direct CO2 emissions because originally that was the title I was given. At the end, I'll cover some of the emissions from the capture process as well. But when we're looking at the emissions of CO2 from the system, we're really looking at the analog of the kind of measurement approaches that are used within natural gas and other systems for measuring methane, in terms of looking at identifying with leak detection and repair programs fugitive leaks. So these are leaks from components and seals which shouldn't be occurring, and you're aiming to identify those and then fix them. We're looking at more site level measurement of the emission rates. So that would be the combined process vents and releases together with the fugitive for a site or area emission. So that's what we would class as a kind of diffuse set of emissions. And of course, there are other systems and other emissions which relate to things like maintenance and repair operations. When we look at the requirements, as I say, we have leak detection and repair. That's the kind of activities in the pictures on the screen where you're going around either sniffing with concentration measurement or the use of optical gas imaging to identify leaking components. We're then looking at quantification at that level. So the kind of things like high flow techniques where you are sucking in the leak and quantifying it. And then site area scale quantification. So the kind of techniques that do site level top-down measurements. And I guess with carbon capture, when we're looking at CO2, there's some specific issues. The requirements, if we look at the kind of leak detection needed under the CCS directive, then we're looking at having a very low detection limit in terms of the emission rates. We have, of course, high ambient background levels of CO2, which is a challenge when you're looking at technologies trying to measure in the ambient air. The dispersion characteristics of CO2 are slightly different, being a dense gas, and clearly there is some issues around what the phase of the contained fluid is, which we've heard talked about with regard to flow monitoring. But there are, fortunately, in terms of CO2 as opposed to hydrogen, many of the similar optical techniques are available for use for CO2. So I'm just going to cover some of the work that we've been doing to develop the capabilities to validate those techniques. So we have at MPL a number of test benches that we can create controlled traceable leaks, and we've used these for validating technologies that are used for methane emissions. And we're currently within MetCCUS developing the procedures and the capabilities to do that for CO2. We have, as I say, a number of different controlled release systems that cover different ranges of emissions and different sizes and scales. And we've done some calibration of those for CO2 and looked at the performance of the system for CO2. And we've done some initial work within related projects and under MetCCUS, where we've looked at the protocols that we would need to be able to do testing of things like imaging cameras that are used for imaging CO2 leaks. And here you can see we've got in the picture there a heated background, because the cameras work on the temperature difference between the gas plume in the background. So we have the ability to create changing background temperatures. And we have a fan there to generate different flowing conditions from a leaking component. So this is a sort of component scale test facility. And we can then look at the detection limits of systems as a function of different performance parameters. And we have as well a system which contains a number of real world components, which we've then configured to have traceable emissions from them. So we can use this system for assessing the sampling approaches that are used for sniffing techniques and the imaging capabilities of cameras in real world conditions. And we're currently basically finalizing test protocols that would work in a CO2 situation. And something we will be producing soon is a sort of review of the different capabilities and requirements for the fugitive and diffuse monitoring of CO2. And the future work within the project will be expanding the scale that we're able to do. There are some issues around getting high volume and high flow CO2 emissions, because of course you very rapidly get cooling and get phase changes. So we are basically upscaling the control systems that we use to be able to do higher level emissions, and looking at heating that in order to be able to get the gas phase emissions. One of our other partners in the project, Force Technology, are looking at site level measurement technique, and there is a tracer correlation method. Within tracer correlation, you release a known emission rate of a tracer from your source, and you also then measure that tracer and the gas of interest downwind. So you rely on the dispersion characteristics of the tracer you've released to be the same as the gas you're trying to measure. And then you can correlate the concentration you see of the tracer with the concentration of the gas you're trying to measure. And from that, you can calculate the emission of the target gas. That technique is used regularly for gases like methane, but Force have been trialing the capability with CO2. And of course, with CO2, you have that higher background. So you need to make sure you've got the sensitivity and the ability to discriminate the emissions you're seeing from other sources and the background. And this is just some initial work that they've done, where they've shown that they are able both to discriminate from other sources, because those other sources don't correlate with the red peak, which is the tracer, and you can also then derive the emissions related on the peaks that you see. When we look at the subsea and storage emissions, we're looking at being able to discriminate very small emissions in an area source, or from small dispersed sources from a ground or from the sea surface, the subsea floor. One of the bits of work that we've finished already was a review by some colleagues at MPL in the underwater acoustics group, who've looked at the technologies and capabilities to do leak detection by imaging bubbles using passive and active acoustic techniques, so sonar techniques. And so that report has identified and has reviewed some of the other projects that have been carried out to look at that and identified some of the gaps in terms of the readiness of that technology to be used in the field to detect leaks. And that report is available. One of the other things that we're looking at in that area is to use the isotopic signature of the stored CO2 to be able to discriminate leaks from atmospheric and other sources of CO2. And VTT have an instrument which they developed, which allows for looking at the difference in the isotopic ratios. And you can see in the diagram there that you can separate out sources which are of different carbon. And that system was currently configured for methane, and we're looking at that for CO2. So those are some of the activities. We're also looking at whether spectroscopic techniques can use tracer compounds to be able to discriminate the CO2. So there's a number of activities to try and drive down the sensitivity for the storage measurements. So when we look at the measurements from the capture process, we are looking and have reviewed the monitoring requirements from the different capture processes, but primarily we're focusing on post-combustion because that's the most common and the most the large number of the current projects are using. But we have also looked at what would be the measurement issues around the other oxy-fuel and pre-combustion approaches. But when we look at post-combustion, and this, thinking back to Aurelé's presentation around some of the SICK instrumentation, one of the issues around the monitoring in the flue gas from post-combustion capture, particularly if it's using amine-based or sorbent, is that you generally have challenging flow conditions. So the flue gas is a lower flow rate than normal combustion. Clearly, we will have low CO2 if the capture process is working correctly, but high water content, generally low temperature, and there are other compounds in there that are of interest to measure. So you're likely to get droplets, you're likely to get condensation. So the actual matrix that you're measuring is a different matrix from normal combustion processes, and we've been looking at the measurement requirements in that space. And that's looking not only at the direct CO2 measurement, but also the associated pollutants that you may get, particularly from amine capture. So one of the things we're looking at is whether direct CO2 measurement post-capture provides a more effective way of measuring capture efficiency than subtracting the input and output flow CO2, because that, of course, is the subtraction of two large numbers. So direct measurement has the potential to provide a lower uncertainty, but you need a sensitive analyzer, not the traditional emission levels of CO2, but down to lower levels. And if we need to use things like dilution probe to dry the gas, then we're looking at needing a highly sensitive analyzer. Now these exist and clearly are available from the ambient field, but there are issues around it in gas handling and gas conditioning. There's also the effect of the post-combustion gas matrix on the regulated pollutant monitoring. You have a different matrix than all of the reference methods were designed for, and so we are looking at what the issues are around this high water vapor, low CO2 issue, and there are issues around things like the dispersion characteristics of that emitted plume as well. So we're currently finalizing a report which is just summarizing the various issues related to post-capture emissions. But one of the things that we are focusing on is the measurement from new pollutants, and particularly things like the breakdown products from amine capture. Also, some issues around things like monitoring compounds like SO3, which is a challenge to measure in that high water vapor conditions. So just to illustrate some of the issues around the sampling and the stack conditions that we have in that post-combustion environment. And we have been developing at MPL as a part of this project and related projects we have the ability to simulate these conditions. So we've identified the range of conditions we want to simulate and how we can simulate these conditions to be able to then test and validate the methods. One of the things that we have done is developed a test bench to be able to look at the breakdown products, so nitrosamines which are forming an amines secondary amines from from amine capture. And in this case, we've developed a closed system that allows us to generate relevant stack conditions with amines in. We originally had considered using our stack simulator, but the health and safety issues of having a nitrosamine solution in a system which isn't completely contained, we moved towards a specific and dedicated system to allow us to test the instrumentation. And when we're looking at nitrosamine and amine methods, we were assessing two candidate methods that could be used, one using sorbents and the other using wet impingers. And this is just some examples of the test kit that we had to test those methods with controlled and known generation of a test gas containing nitrosamines, but with a matrix which is relevant to the post-capture matrix. And we carried those out with a sample containing 8 compounds for the initial tests. And what we've done is look at things like the sampling capture and the capture efficiency. And one of the challenges is that across even this limited number of nitrosamines, you have a wide range of different physical conditions. So we have different vapor pressures, we have different structures, we have ring and straight chain structures. And so the challenge is the methods and the issues around, for example, the capture efficiency from these impingers. So we're drawing the sample through a wet solution and collecting them in that solution for subsequent analysis. And we put a cartridge on the back end, and we're seeing breakthrough of the more volatile compounds, and then we're seeing sticking of the heavier compounds in the sample chain. So it's a very challenging matrix or set of compounds to measure. And we've been looking at the performance of the method across a whole range of compounds. And we've done both lab tests and also some limited field tests. But what we can see from here are things like, here we're looking at the third impinger. So we're seeing that for the lighter nitrosamines, they're more prevalent in the final impinger, which means they're being carried through the first. And so we are defining the controls and the quality control on the method to ensure that we get capture across and within those impingers, and what quality control procedures we need to check that you don't have loss throughout the end of the impinger train. And there's a whole range of other factors within the method that we're investigating to do with sample handling, how you manage the samples after you've collected them, issues around with the flow rates, impinger design, etc. So there's a whole range of issues which we will be looking at within MetCCUS. But the intention is at the end of it to have a draft method which we'll put forward into standardization. But as we see, we're actually seeing recoveries that range from low recovery because of high volatility through to issues that may be with the analysis lab when we're seeing more than 100% recoveries. And just the whole range of physical parameters and the shapes, ring shapes, etc., are affecting the sampling. So it's a challenging method. And of course, for different capture processes with different capture solvents, the list of nitrosamines that maybe need to be monitored can be quite high. So we need to ensure that the method is appropriate for a whole range. We're already looking at potentially additional methods to deal with the very heavy nitrosamines. Just to touch on another, so this is work which is feeding into MetCCUS, but I thought you might be interested in it. It's some work that we actually did also within the decarb project, where we've been looking at the monitoring of CO2 using our optical LiDAR system. And so I just sort of mentioned this system is a remote sensing laser radar system that lets you image the concentration of a plume in the atmosphere by scanning a laser beam around. And we did some work to basically identify the spectroscopic region which would be optimum for measuring CO2. And we deployed that at a site with just, it's not a CCUS site, it's just a site with CO2 emissions, just to look at what the capability was to be able to detect remotely CO2 plumes. And we compared that to some in-stack measurements done using our stack monitoring team. And from that, and we've just published this, we were able to show we can image and detect CO2 plumes, and comparison of that to the in-stack measurements gave very good results. So it's just another potential technique for some of the area emission measurements. So just in conclusion, within MetCCUS, we're looking at a number of the emission scenarios and developing the methods and the capabilities to validate those methods with the intention to feed that through to guidance and standards. And of course, we're always welcoming and requesting input from the stakeholder community around emerging issues and things that are important to you. I asked an AI bot to generate those cartoons of what the measurement problems are for emissions from carbon capture. So I think I'm not too worried about AI taking over my job just yet, but certainly whether AI will help us in the future is an interesting question. So thank you.
Thank you, Rod. Interesting presentation. Are there any questions for Rod?
Hi, David.
David,
hello. Well, I'll move the screen so you can see me. I don't know if I've brought this up before, but thinking about the gas turbine case, if we have capture on a gas turbine plant, the CO2 in the flue gas drops from about 5% down to about 0.25%. So quite a low level. And at that level, the contribution of the CO2 in the air that comes into the system becomes significant.
Yep.
And there's a question of how to correct for the background CO2 in the combustion air. So I'm just wondering if that is being considered in this project.
In terms of, we're looking at the measurement requirements. So yes, the kind of measurements you might need both post capture but also pre-capture to be able to assess the removals, and that whether that includes then also the ambient measurement as well. So yes, it is something that we've and of course, as you're aware, we also have associated issues like what the reference conditions are that we would then be reporting things on when you've got things like capture on the back of turbines. So there are a number of issues that are coming out of the woodwork related to monitoring post capture.
Yeah, I think ETS, the trading system, is a little bit confusing on this because it talks about inherent CO2, but I wouldn't count this as inherent CO2. I think it's transferred in effectively.
Yeah. When you're looking at the balance gas that you have, or your combustion air, then yes, it's something that needs to be accounted for.
Yeah. Thank you.
course, if you get good enough, you could class yourself as a DAG.
Yeah, like with particulates.
Thanks for the first question. We have one more in the chat. I don't know if you had a look already, Rod. It's about the issues with SO3 measurements.
Yeah, the challenge is that it's a very, very fine, and it'll pass through a lot of the capture media. So there's some issues around. You can end up with a very fine mist. That is exactly the issue.
Mm-hmm. And what about the time scale for having formulas for emissions with respect to LDAR? That's another question. So
in terms of the capabilities, then that would be the protocols, I think, and Iris will probably correct me, but I think we're looking towards the end of the project for the final sort of methodologies. But certainly some of the assessments we'll be doing of the equipment and things like the how we can assess the cameras will be available earlier in the project.
Thanks, Rod. I think we have time for one last question. Perhaps Jan, who is raising the hand.
Yeah, hi, Rod. I think I missed one of the last few slides. Did you, will your truck system actually do both LiDAR and dial measurements?
It is basically a dial system.
It is a dial system. Yeah. But you compared it to LiDAR, didn't you?
No, I basically just said it was based on LiDAR.
Okay.
So okay. It's, but we are doing differential absorption, so yes, we have a concentration measurement from it. What we compared it to was in stack measurement of the CO2 emissions.
Yeah, I think you need dial there. Yeah. Otherwise, you don't get the big background.
Oh, exactly. Yeah.
Yeah. Okay. Thanks.
Okay, thank you very much once again, Rod, for being available today to present about CO2 emissions monitoring and also partially what is being done in this regard in the MetCCUS project. I think we can move on to the next speaker in our agenda, who is going to talk to us about CO2 specifications for transport and thermodynamic properties of CO2. Roland, welcome and thank you for accepting the invitation. Do you prefer to share yourself the screen or do you want me to do it for you?
I can share my screen. That should work better.
Okay, perfect.
Giving commands. Yeah, hello everybody, and thank you for the opportunity to talk to this group. We are members of this project. We are doing work in the project. But I'm talking, well, more about from different positions today. So let me share the screen. Need to share this one, and then okay. Now you should see the slide. Is that correct?
Yes, we can see your screen.
Good. So I'm talking here today in two different functions. The first one is sub-project leader for CO2 transport in the European Energy Research Aligned Joint Program CCS. So that's essentially when I'm talking about CO2 specification for transport. And then in the second part, I'm talking in my role as chair of thermodynamics here at Ruhr University, Bochum, and that's the position in which we are members of this or part of this project. And that's when it comes specifically to thermodynamic properties and existing models. So let's see. You will also see that the style of the slides changes throughout the presentation. So that's how you can identify whether I'm just talking on purpose of ERA CCS or as chair of thermodynamics. But let's start with the transport of CO2 first. The background of what I'm reporting about is that on a European level, DG Energy aims at the development of a European transport network. They want to have discrimination-free access, and they are thinking in terms of a regulated asset basis and multimodal transport. So regulated asset basis, I would say essentially because this is what they have experience with from CO2, from natural gas and from power. So they are more or less rolling out these measures as we know them from the other transport grids. The reason why they do, in my view, is that politics is concerned that structural disadvantages result from the fact that a part of the industry with hardly avoidable CO2 emissions is located far away from shore. And so they are expecting structural disadvantages for regions somewhere in the middle of Europe, in Central Europe. And that's, of course, something politicians want to avoid. So that's why politics is highly interested in Brussels in developing such a CO2 backbone. What has changed over the last few years, in my view, is that industry is largely in the driver's seat by now. So in that respect, the situation has changed. So industry is pressing for fast development of fast decisions in order to be able to develop their own plans how to handle CO2. The whole development at the moment is, I can say, quite dynamic, and standard network codes for transport are correspondingly urgent. We do have, of course, CCS projects, and there are specifications for CO2, particularly for the impurities in CO2, but they are project specific. And in some countries, we see the development of national standards. Here in Germany, the DVGW is leading corresponding initiatives, but they are pretty much focused on pipeline transport. This is the background against which an expert group on CO2 specifications was established as a spin-off of the CCUS forum process. In the beginning, I think DG Energy had the idea that this expert group could establish something like standards for CO2 composition, but already in the first meeting, it was obvious that this is not the case, because for standards, we have established organizations. We have in Germany DIN, we have ISO on a global scale, SEM on European level, many other national and international ones. So it couldn't be about the development of a standard. We just didn't have the mandate for that. The goal we formulated was that it's about pointing out issues that have to be considered by standards and making suggestions for how to formulate these standards. And the whole discussion was a difficult balance between sending the message, yes, we can and must go ahead now, but at the same time pointing out that there's still a lot of knowledge missing for an optimized operation of CO2 grids. Now the report from this expert group was completed end of June, and it was finally published online September 22nd. So you find the link here under which the report is available. Just briefly a look at the structure of the expert group. There were few more colleagues who joined the group later on, but what you essentially see is that the group was largely governed by colleagues from industry. So I'm from academia. There were a few more colleagues from academia, but most of the active colleagues in in the group actually came from industry. And beside me, Andy Brown and Harald Tadlik were the chairs of the group. The report that is available by now is structured into 5 chapters. Introduction, of course, giving some background, assumptions and nomenclature, giving also the background. And then the first, I would say, interesting chapter is the chapter of impurities. By far the most extensive chapter, specific considerations for the different transport modes, for storage. So not really a detailed analysis of storage opportunities, but a reflection in how far geological constraints have an impact on impurities for transport. The relevance of the different capture technologies for transport. So what is the influence of the capture technologies? And finally, one chapter or one section on port infrastructure required for applications where CO2 is captured on ships. In principle, we agreed on 3 guiding principles for the formulation of CO2 specification, impurity specifications, whereby I would like to add one. So let's say 3 + 1 guiding principles. The first one is obvious: 2-phase flow should be avoided wherever it is possible. Second one is also obvious: the formation of corrosive phases must be avoided. The third one is that the concentration of all impurities in the CO2 should be low enough that the health and safety impacts from carbon dioxide itself are the dominating ones. Simply against the background that if you just imagine a permission process, it will be difficult enough to get permission for building a CO2 pipeline. But if you have to discuss every single impurity in the stream with official sites, then getting a permission will become at least very complicated. And that's why the idea is to just limit impurities with a significant health and safety impact to levels that are low enough that we can always say the CO2 itself is the dominating factor. For me as a scientist, and probably also to the metrology community, it's important that the given limits on impurities should be science-based and traceable, at least with a rough estimate on uncertainty. And that's, I have to say, not yet the case for the levels which are handled. With regard to impurities, there was one interesting distinction, and that's the distinction between non-negotiable impurities and negotiable impurities. Now, non-negotiable impurities are those impurities that lead to a formation of solids, that lead to corrosion, and that's mostly water and other impurities that have an impact on the water dew point, or on the dew point, well, or bubble point, well, on any, let's say, on any formation of a second phase in CO2, depending where you are, whether you are in the gas phase or whether we are talking about high density, or whether we are talking about saturated liquid. But anyway, so water and other impurities that lead to the formation of a second phase need to be limited to levels that no corrosive second phase can be built. And poisonous impurities have to be limited to the levels which I just discussed. So that's the part of the impurities that's non-negotiable. But then there are also negotiable impurities, which are essentially, I would say, the so-called non-condensable gases. So that's nitrogen, that's to a certain degree argon. Oxygen typically is limited to very low limits to be sure for the oxidation issues. It can be methane, depending on the processes that feed in, but it can also be hydrogen. And high concentrations of these components increase the cost of transport. But on the other hand, limiting them to low values increases the cost for CO2 processing. So at that point, an optimization of the allowable limits should consider whole chain cost, which is very difficult, in fact, because we don't know yet what the chain will look like. So how much of the CO2 will be transported in tanks before it goes into a pipeline? So if you have imagine a system where most of the CO2 is transported by tank to some hub where it goes into a pipeline, then it's reasonable to have very strict limits on non-condensable gases, because they have to be removed for tank transport anyway. If you have a system where you have mostly pipeline transport in first instance, it makes sense to allow higher limits of these negotiable impurities and remove them wherever they are liquefied for transport for the first time. So at that point, we need common standards for the backbone, but where the optimum is not clearly to be distinguished. Well, not clear so far. We'll have some compromise at that point. When we talk about levels of non-condensable gases, it's slightly difficult to deal with them. So far, it was usually that the limit of non-condensable gases was given by the required purity of the CO2. So if you require a CO2 purity of 98%, you have more or less 2% allowance for non-condensable gases, because all other specific limits are usually in the ppm range, so orders of magnitude smaller. What is important is the pressure on the saturated liquid line for tank transport. So when we think about medium pressure ship transport, rail cars, but also for the design of pipelines. And at that point, well, usually in most cases, nitrogen is the non-condensable gas with the highest impact on the location of the saturated liquid line. The impact of argon, oxygen, methane is slightly smaller than the impact of nitrogen. So at that point, it may make sense to say, okay, we have 2% for the sum of non-condensable gases. However, if we have hydrogen in the system, which is quite likely if we have blue hydrogen production at some point, then we will have at least traces of hydrogen in such a CO2 backbone. The impact of hydrogen is much larger, let's say roughly a factor of 3 larger than the impact of nitrogen. So it becomes difficult to limit the total impact on the position of the saturated liquid line by only specifying the composition or the minimum purity of the CO2. But it's also difficult to define limits for the single single components. If you allow, for example, for 0.5% hydrogen, and you want to have a limit that's equivalent to 2% nitrogen, you can only allow for 0.5% nitrogen. If you have 2% nitrogen plus 0.5% hydrogen, then the effect is roughly like 3 or 4% nitrogen. So at that point, it becomes difficult to define limits. And from the chip community, there's the suggestion to define the minimum temperature required for liquefaction at a certain pressure rather than composition, which makes sense because that's what you are really aiming at. And in a similar way for pipeline transport, one could limit the concentration by giving a maximum pressure on the saturated liquid line. But the problem is that in pipeline, compositions will be measured, not saturation pressures. And so if we want to go that way, we need somehow a standard for the conversion from measured composition to a corresponding pressure on the liquid line. The other way around, the conversion will never be possible because the same pressure on the liquid line, saturated liquid line, can result from a different composition of non-condensable gases in the CO2. But in one way, if we measure the composition in the pipeline, we can deduce the pressure on the saturated liquid line, and to do that, we would need somehow a standard. The whole report also addresses research areas where the group saw relevant room for improvements for the optimization of this system. And you will recognize many of the areas which are dealt with here in the MetCCUS project. So that's flow and composition measurements in 2 phases. The fast online composition measurements. Some UK studies asked for sub-second online composition measurements, which would rule out gas chromatographic measurements. So there's room for research and also discussion what actually is necessary. And then one point which, well, I wouldn't mention to the outside at the moment. That's the question of the hazardous impurities. We do have limiting values for all of the components. We know what is the allowable concentration of carbon monoxide, of SO2, whatever. But I think we know very little about the combined health impact. So what is the impact of carbon monoxide when people at the same time are exposed to a high level of carbon dioxide? So questions like that are not really answered as far as I know. Then there's one issue that's still open, is the effect of acid-forming impurities on phase equilibria at ppm level. There is some knowledge on that, of course, but details are lacking. We don't know what really happens with chemical reactions in mixed CO2 streams. At pipeline conditions, most reactions should not take place, most possible reactions between impurities, but we cannot tell what are the catalytic effects in a pipeline, and do we have to expect reactions which do not happen typically under the conditions in a pipeline. Then we have the question of liquid-liquid equilibria and solid-liquid equilibria at low temperature. And that's particularly relevant for glycols and amines. We know CO stress corrosion cracking, but how about mixtures of CO, CO2? Does the CO2 increase the risk of CO stress corrosion? One question that came up, do we actually need to have a corrosive phase for corrosion? Isn't it possible that an adsorbed layer on the wall of a pipe can already cause significant corrosion effects? And finally, we agree, or we thought that we need a system analysis which combines CO2 transport, also considering the impact of impurities, of course, with aspects like hydrogen transport and the regional availability of renewable energy, because this will become important when you think about well, yeah, capture systems that need a lot of electric energy, like oxy-fuel technologies in cement plants. They make only sense if they have green power available. And the question is that regionally available? So our colleagues working in system analysis need to think these different areas together in order to come up with scenarios for what an optimized system may look like. There is the obvious need for European standards if we want to have such a European backbone. What we see so far is that specifications for impurities are mostly project specific. We do have countries that develop national standards. I already said that DVGW is working on that in Germany, focusing on pipeline transport. And usually the national standardization bodies are well connected to ISO. So there are mirroring committees on the national level. And ISO is working on standards both for pipeline and for ship and tank transports. But you know that ISO standards are usually very general. So they will not be detailed enough as basis for development. And the SEN process could lead to a more detailed standard. But initiating such a process will cost much time. Industry is pressing on the basis for investment decisions as soon as possible. So what we try now is to align national initiatives to make sure that we have a common understanding in the different countries, and in that sense develop a basis for a SEN standard which can then be installed later on without having to be afraid of large surprises. One disadvantage in my view is that the development of standards for pipeline and ship and tank transport is largely independent of each other at the moment, and there are different communities involved. So synergies for an optimal system might get lost at that point. An ISO standard for pipeline transport will likely contain a value for the minimum purity of CO2. It will not contain a list with strict limits for certain impurities. At least that's the status of the discussion at the moment. But it will contain an appendix with examples for practically feasible composition. So the more detailed steps really have to come on a national level. An open question to me at that point is how to deal with impurities that are not specifically listed. So if we take Northern Lights as an example, they take a relatively extreme position. They claim that substances which are not listed must not be contained, And that approach is already very challenging for a project that comes up with contracts customer by customer. But in my view, that's not a feasible approach for a European CO2 network, because if you feed in CO2 from very different processes, you will always have a broad variety of trace components in the CO2. Some of them probably in a ppb range, but not zero. And some of them may simply be below the current analytical limits, so that we assume they are zero, but in a few years with improved analytics, we may realize, hey, wait a moment, it is in. And so not having impurities or other impurities than those listed in the flow is a critical point of view from, I think, because it may become a challenge for investment maids now when analytics becomes better in a few years, or if we simply start looking at components we are not looking at the moment. So we somehow need to come up with a reasonable approach how to deal with impurities that are not specifically listed. Okay, maybe I can go for a break at that point and ask for questions before we go briefly to the thermodynamic properties.
Thank you,
think
Roland.
I almost spent my time on this part. I think.
Yes, unfortunately, we just have 5 minutes left, but if you would like to use these 5 minutes to show something very concrete on the thermodynamic properties, or if you prefer not to talk about it at all, then that's fine.
I can just show a few slides on it.
Sounds good. Thank you.
Sorry for, but it's too interesting. The topic is just.
It is.
So let me try to share again. Okay. And now change that. Okay. So thermophysical properties of CO2-rich mixtures. I talked a lot about the impact of non-condensable gases, and this is something we can predict relatively well today with relatively high accuracy. What you see is that mostly the saturated liquid line is impacted by non-condensable gases, and that's important. Well, obviously for the use of centrifugal pumps, but the main point is that the arrest pressure to avoid running ductile fracture depends on the pressure on the saturated liquid line. So if you have this case here with 10% nitrogen, you see that at 200, let's say 270 K, you have to expect something like 8 megapascal pressure on the saturated liquid line. And that's the pressure you have to design the pipeline for against running ductile fracture, while at just 1% CO2, you are down to something like 4.5 megapascal. So that's why the amount of non-condensable gases is a big issue for pipeline design, and in a similar way, of course, also for tank transport. These models, well, these things can be described. So there is, since 2008, there is a standard coming from the natural gas community, an equation of state that describes up to 21 components and which already contains many of the components we know from CCS applications. And that's essentially, well, a 4-parameter corresponding states approach, which is supplemented by a departure function to achieve higher accuracy. So this equation is defined as a standard for natural gas properties in ISO 27765. However, in this equation, CO2 has always been considered as a minor component. So the mixtures which were in focus were natural gas mixtures. And well, water is relevant, the water dew point is relevant, but nobody ever cared for the water-rich phase. So how much methane is in the water-rich phase? If we think about CO2 capture, this is now important for the CO2 slip. So we need to be able to also describe other phases and other main components. And this work started about 10 years ago when we published the first version of the CUS-CG system model, where we considered CO2 the main component, or we looked at CO2 as the main component with mixtures with other relevant fluids. And in a nutshell, you can say for gas phase transport, in the gas phase, the GERG 2008 model is okay, and other simpler models usually yield relatively good data as well. If you look at the liquid phase, so then you will realize in this CO2 water, in this case, that it's only those models which are really designed for CO2 as the main component yield very good results or reasonably good results. And that's also true here for the phase equilibrium description. So in the system CO2 water, that's one of the most demanding systems where you have VLE and liquid-liquid equilibrium, everything you need to describe. And most systems here simply fail in the description of the liquid phase, so of the water-rich liquid phase in this case. If we come to minor components, well, yes, minor components are important for CO2 transport, but they are mostly important for phase equilibrium. So the location of phase boundaries is impacted by minor components, even in small concentration. So it's important to describe this VLE behavior. But these components do not have much impact on homogeneous data. So this is mostly about VLE. What we can show is that this kind of models, it's also possible to describe more exotic systems. In this case here, MEA with water in the homogeneous region quite well, provided there is sufficient data available, which is not the case for many of the systems. So where we are by now is that there is a whole set of impurities considered in this kind of models. So that's the status of the matrix for in a paper which has just been submitted to cryogenics. And so you see there are even some amines included in the matrix by now. Hydrogen is included. So this has quite a bit extended. But you also see, if you look at how these systems are described, so the yellow dots here, those are the ones which are described really with reasonable high accuracy, where we have this departure function. Most are described just by adjusted reducing functions. So we have to simply rely on a fitted corresponding state system. And others are described simply only by combining rules. So yes, a lot has been achieved, and these systems can be described with relatively high accuracy, but there's also still a lot of work today to do. And that's essentially our part here in MetCCUS. Within MetCCUS, some of these systems will be measured, and we will use these data to further improve this framework of equations of state here, to be able to better describe the relevant CCS mixtures.
Thanks a lot. Thank you, Roland. I think that it was very interesting, and you were able to give 2 presentations. So that's really appreciated, your contribution. And yeah, there is no time for questions, unfortunately, but if people have questions, please, you can write them in the chat, and this can be addressed directly there. Thank you once again, Roland, for your time.
Yeah. And there is the link, well, you will distribute the slides, and there is the link to the report I initially talked about. So whoever is interested in this report is able to download it.
Perfect. Thank you very much.
You're welcome.
All right, so moving on, in the program, we now have Martin Carré and Lucy Chauvet from Liquide, who are going to talk to us about the CCUS process and metrological challenges from an industry perspective. I can share my screen right now. Is that okay for you, or you prefer to do it?
No, you can do it.
Okay, perfect. Okay, so I found it here. Once again, thank you for accepting the invitation, and I let you introduce yourselves. The floor is yours. Thank you.
Thank you so much. So my name is Martin Carré, scientific director in Liquide R&D. So afternoon.
I'm sorry to interrupt you, Martin, but your sound is really low. The voice is not very well transmitted. So if you have maybe some headsets or a microphone that can allow you to speak louder, please, that would be great.
Okay, so is it better now?
It's
Much
perfect
better.
now.
Yeah, okay. So again, good afternoon, everyone. My name is Martine Carré. I'm Scientific Director in Analytical Science and Quality within Air Liquide R&D. And I have a pleasure to present this topic today with my colleague, Lucie Chaubet, who is a pole manager on a low carbon hydrogen study. So I will start the presentation with the next slide. So we will start by a short introduction of Air Liquide R&D, a short one, and then Lucie will continue by a presentation of our CCUS solution, and also coming back to the impurity management, which is already a topic discussed in the previous presentation. And I will finish by the metrological challenges that we have in industry for the CCUS application. So in the next slide, so I will come to Air Liquide R&D. And so just for the one who may don't know Air Liquide, we are one of the world leader in gases, technology and services for industry and health. In industry, we are focusing more and more on sustainable solutions for a wide range of industrial processes, for example, energy, food and chemicals, but also for transportation. In health, we have a large portfolio of solutions for patients at home and also for delivery of medical gases in hospital. And we also supply a specialty ingredient for vaccine, for example. In the next slide, I will go deeper in the R&D key figures. So we have 5 campuses, main campuses, and I will come back to that after, with 3 satellites. We are roughly 560 employees with globally at the worldwide level for R&D purposes. And 60% of our projects are conducted in partnership with academics, but also with customers. So we do a lot of work in collaboration. And we have 60% of our portfolio, which is devoted to reduce the CO2 emission, and including the CCUS project. And we are working in the limited number of molecules, because only 18 molecules are already in our portfolio, taking into account all the application of this molecule. Of course, CO2 is one of them. In the next slide, I will show the different localization of our innovation campus. We have 1 in US and 2 in Europe, 1 in Frankfurt, where is based Lucie, and 1 in Paris, where I'm based. You have also 2 others in Asia, in Tokyo and in Shanghai. We have some satellite, meaning some team, R&D team working within academics laboratory, for example, and then which are linked to the main campuses. Each of these campuses have some dedicated topic to work on, and the one who work the most on the CCUS application are the one in Frankfurt and in Paris. And so in the next slide, you can see more in detail what we will do and we do in our innovation campus in Frankfurt. Indeed, we do a lot of scientific study using experiments from lab scale, but also from a larger scale, in order to be closer to the final operation mode in industrial part. And we use also some tools like a life cycle assessment, and we have some experts on that field in order to identify the best solution to reduce the carbon emission for us and also for our customers. Of course, the main molecule we are working on in Frankfurt are CO, hydrogen, and CO2, of course. In the next slide, you will see more about our innovation campus in Paris, where we have a lot of laboratories with different competency and technical platform dealing with safety, process engineering, also computational and data science, material qualification, combustion, food production, additive production, and gas analysis. And some part of this platform are used for the study on CO2 application and CO2 capture and sequestration. So in the next slide, I will leave the floor to Lucie for presenting our CCUS solution.
Thank you, and hello to everybody. So I will present to you the portfolio of solutions that our engineering and construction is proposing. Reminding first very generally the CO2 value chain, because it has been presented also earlier today. Reminding that the flue gas can be very different in terms of composition according to the type of industry that we are talking about. So several types of carbon capture processes that can be applied and that must be adapted to the concentration of the CO2 as well as the other impurities that we will have. And also according to the utilization type or sequestration and specifications that come from the transport. In the next slide, I will talk about the value chain, particularly for Air Liquide. So we are a technology developer and have a department of engineering and construction that proposes several types of technologies of CO2 capture, depending on the CO2 concentration and purity target which will be proposed. And we have been operating CO2 plants for several decades. So there is a large expertise in the fields of CO2 compression, liquefaction, and CO2 storage, as well as operation of CO2 pipelines. And this is one of the transportation methods for the CO2. Air Liquide is also active in the shipping of CO2 with several projects, also with the ship manufacturers. And the strategy for Air Liquide is to be able to propose carbon capture as a solution, as a service for our own plants, which are emitting CO2, as well as for our customers to help them in their way of decarbonization. For ourselves, the target is to reduce emissions by a third until 2035 and to reach carbon neutrality until 2050. Here on this slide, we have the graph of the CO2 content in the feed gas versus the CO2 product purity target, and the different products in the portfolio are represented on this graph. So the absorption is the main technology and the most mature one that we will propose for diluted gases from very low concentrations until around 15% for the low pressures, and at higher pressure it can go up to around 40–50%. And then all the other products are branded under the names of CryoCap. So CryoCap Oxy, it's for a gas after an oxy combustion. CryoCap H2 for our steam methane reformers, and cryocap flue gas is the solution that we will propose for the gases with above 15% of CO2 in the feed gas and the low pressures of the gas. We can go to the next slide, where I will give a bit more of detail on the cryocap flue gas to illustrate the process. So a flue gas will have a pre-treatment and be compressed, cooled down and dried before going to an adsorption step. In this adsorption step, already some non-condensable gases are separated. And after further compression, the gas will go to a cryogenic liquefaction of the CO2, which will as well separate some non-condensable gases. And this is a process that we can propose for a wide range of capacity from 400 tons per day to around 5,000 tons per day, with quite high capture rates from 90 to 95%. Then in the next slide, please, are some references of projects for which we have made proposals. So Sainte Geneviève is in the US. These are projects selected from cement and lime applications, which we think is quite relevant for the MetCCUS project, because these are flue gases or off gases that have a large panel of impurities in high concentrations. The last project, ECIOM, is also interesting because this is a conversion of a cement plant to oxycombustion, and this enables to have a quite efficient capture of the CO2 by already pre-concentrating the CO2. I will now move on to the topic. To complete the value chain, we have the involvement in several projects of sequestrations and sink developments. So many of those have been mentioned before today, with the project Northern Lights, and in the port of Rotterdam with the project Portos, as well as Antwerp. So our role as Air Liquide is to evaluate the CO2 capture technologies and the transport. And in the case of Portos and Antwerp, we are also in contact with our customers who are also CO2 emitters. And our role is to aggregate the different CO2 streams, to liquefy disaggregated CO2 streams, and before transport to the sequestration sites. Here in the impurities management, in the first slide, I will give a short overview for several types of gases of the type of impurities that we have. So we have a database internally from our contacts to customers of the types of impurities that are included in those gases. Here I made a very summarized overview of these types of impurities. For example, in a refinery flue gas or in a kiln off gas, you are in an oxidative atmosphere. So the sulfur and nitrogen compounds will be in the form of SOx and NOx. Whereas in steel blast furnace gas, you are in a reducive atmosphere, so more in the form of H2S and COS. In cement off gas, ammonia has also been measured, as well as HCN. And metals is a large panel of different components that can be included. Next slide, please. This slide has an animation, so maybe you can click several times to show all the 4 bubbles. When we design our processes for CO2 capture, we have to think from the CO2 source all the way to the storage and utilization, and to optimize the solution for the management of the impurities. So starting from the knowledge of the specification to be achieved and the composition in the raw gas, but also how dynamic, how is for each impurity, how it is behaving in dynamic mode. Do we always have this level of impurity, or are there at some points peaks where this impurity will be at higher concentration? This implies knowing well the process of the customer. Like, for example, in cement industry, they work with some batches. So you can have an impurity that for a short period of time will be at a much higher level. This needs to be well known for the design of the impurity removal. And then according to the carbon capture solution selected and the temperature and pressure that we will have there, we need to know well for each impurity how it will behave in the carbon capture. Will it leave with the CO2 depleted gas, or will it remain in the CO2? How will it behave with the sorbent, or in case of a cryogenic purification, will we have phenomena of freezing of this impurity? This needs to be avoided to avoid plugging of the equipment. In processes where we have recycle loops, we must have good simulations to ensure that we will prevent the accumulation of the impurity. And when you remove part of the gas, of course, in the CO2, there will be a higher concentration of the impurity with the fraction of the gas that remains. And this knowledge of all these phenomena related to the impurities will help us decide which impurities are to be removed upstream the carbon capture or downstream. And to make the solutions cost effective, we need to know quite well these concentrations. Otherwise, we can over-design the impurity removal solutions. It's also quite interesting for the process engineer making the design to understand why these impurities have specifications. So starting from the specification for the usage, of course, for food and beverage, you have quite a number of norms to respect safety and sensorial aspects, which are very important. If you are talking about synthesis of methanol from CO2, then there are catalysts involved, and we need to avoid the presence of impurities that will deactivate the catalyst. For some applications of enhanced oil recovery or storage, where you could think it's less restrictive specifications, actually there are also phenomena of inflammability risk that needs to be avoided, the impact of the impurities on the well or on the concrete, and miscibility with the oil. We have to avoid the formation of acid and hydrates. And the transport itself is often dictating the specification because the corrosion of the transportation materials needs to be avoided, but also in case of leakages, the toxicity of the gas may not be increased by these impurities.
So I will continue the presentation just to show you, based on what was presented by Lucy, what are the metrological challenges that we may face today and in the future. So coming back to the sources, it was said several times during the day that the variability of a raw gas composition is quite an issue. So it's even more important at the moment than the way to measure it. So we need to be sure that the different components that are present in the gas are measured correctly. So how to ensure the reliability of the analytical method is one question, and we are working on that. So you can see on the graph above, we did, that was the part of the database mentioned by Lucy, giving some range of concentration, component per component. So we aggregate all the type of sources in order to have a full range of concentration for each component. And you can see that in some cases the variation, so it's in the log scale, so it's really a huge difference. And you can see that in some cases we may have up to a factor 1000 between low concentration and high concentration of this impurity. So developing reliable analytical technique is an issue, especially if you want to have the same techniques for covering all the range, but also having reference gas mixtures in CO2 matrix and CO2 matrix with the other measure impurity is also a key topic. But as it was mentioned before, it's something which is a request and in which we will work during the MetCCUS project. In the next slide, I will come back to the challenges during the process itself. Of course, again, the flow rate. Flow rate is important and must be measured correctly in order to design our processes, and we need primary flow standards for that. Also the material compatibility, and it was already presented, and we agree with that challenges, which is key for us. And again, the control of impurity online, which may be necessary to avoid any damage during the removal of impurity and in the process. So in the next slide, I also come back to the final challenges, which are for the transport, storage and utilization. And like it was said by Lucy, for some utilization we have clear specification, but for some other we don't. So we need to have more visibility on the specification that may be request. And also we have to take care of a leakage during the transport and the storage. And so having a way to measure the emission of during the process is important, and to have reliable data also. So in conclusion, in the next slide, I just would like to say that we are part of and partner of the MetCCUS project, and it's also because it will address some of our industrial challenges, and I just summarized the 4 work package which are dealing with our industrial challenges, so the flow, the measurement of emissions, also the formation and the production of reference material, and the thermophysical properties, which are useful for the modeling of our design. But I would like to say that it's only the first step. We need to address other challenges, and raw gas analysis is also a key topic to work on, and it was mentioned several times during the day. But also online control, because we may find analytical method in laboratory, but having online sampling system and analytical tool are not obvious with this type of composition. So that's what we would like to share with you today, and we are pleased with Lucy to answer to your question if you have any. Thank you.
Thank you, Martin. Thank you, Lucy, for taking the time and sticking to the time that was supposed to be for you. We still have a couple of minutes in case that there is any question. Please feel free to put it in the chat. There is one question. What do you mean with raw gas?
Raw gas for us is the gas directly at the sources where we will take the CO2 before the purification and the transportation. So it's really coming from the industrial plant.
Thank you. Any other questions from the audience? There is a couple of questions. Is cryogenic capture expensive in terms of energy?
I will not say there is no consumption of energy. Expensive, it depends of comparing to what. So I would say that this solution is, in some cases, the only one which is available for removing some impurities. So, of course, the full solution is expensive. And we are working to find a way to reduce the cost. And that's why it's important also to have a clear knowledge of a concentration of impurity to adapt the cost to the real needs.
Per ton of CO2, we are around 400 kilowatt hour. And in some scenarios, this is competitive towards other solutions when, for example, amine wash consumes a lot of vapor, depends of the prices in the region.
Okay, thank you. And there are two questions, but they are both related to the raw gas mentioned at the beginning. So if you can say if there is a list of key impurities in this raw gas, or what will be the composition of this raw gas and or the purity of the CO2 in the raw gas?
But in fact, that's the part of a slide that I presented. In fact, we have a lot of different raw gas composition. So we would like to have a standard raw gas, but it's not the case. So it's really dependent on the type of industry emission. And so there is a long list of impurities, so I cannot give it now. And you have seen in the slide that there is a lot of range of concentration of this impurity. So that's really the issue that we have.
Mm-hmm. Perfect. Yes, understandable. Thank you. Just to make sure, which was the slide that you mentioned with the list of impurities? Was it at the beginning?
But there is the slide presented by Lucy, and also I don't remember the number, but where there is a list, a table with the different impurities depending on the raw gas. Yes,
this for example.
Yes, exactly.
Perfect. Okay. I think that it's already time to move on with the program. So once again, thank you. There are, I think, maybe one more question in the chat. If you can have a look, please, afterwards and address there directly these questions. And thanks for this presentation. I suggest that we have a coffee break and come back at 3:45 p.m. Central European time. Thank you.
Thank you.
Thank you.
And please don't hesitate to contact us if you have more questions.
Thank you.
So we will resume in around 12 minutes. Hello, Christopher. Thank you for joining. Just to make sure
Hello
that Good to see you, and thanks for joining. We say that we are going to have a coffee break, so we will be back in 10 minutes to start with your presentation.
Okay, that's fine. Maybe you can help me use this for giving the presentation. So I need to click on Take Control.
You can click on Take Control, indeed, and you can move the slides directly using the Teams application. That's one option. The other option is for you to share your screen directly.
Okay, so I don't have to do both. I can just do the share, and then that will share my screen.
Yes, you can do that if it's easier for you, or we can do it for you if there is any problem. So
okay, yeah, and certainly you can help me along in case there are any technical problems with that.
Sounds
I'll
good.
be using a PowerPoint presentation, probably like everybody else has been doing.
Exactly. Okay, Christopher, let's do that, and yeah, we resume in 9 minutes, more or less.
Okay, sounds good. I'm here.
Thank you.
Hi, Christopher.
Hello there.
Christopher, do you see my face? David Vegamaza here.
I'm sorry? Ah, David, oh my God.
Christopher,
Great
my
to
dear
see your face
Christopher.
again. It's been such a long time.
Such a long, long time, my dear friend. Be careful that there are lots of people listening to us right now.
Okay. Anyway, well, hopefully
happy
you'll be
to see
coming back
you.
to NIST sometime.
Yeah, I have to. I want to. I will do very soon. I will do it very soon. You are the same. You haven't changed.
Oh, thank you. Thank you.
Look at you. Hi,
Anyway, I am going to need to concentrate right now to see how I can load my presentation.
Yes, don't worry. I just shut the fuck up. Don't worry. Fine.
Okay.
Bye-bye.
Let's see what we have here.
Yes, if you want to start trying already, Christopher, to share your screen, please feel free.
I am seeing it right now. Are you?
Yes, I can see, and now it's full mode.
Okay,
exactly.
excellent. Okay,
Yeah,
let me
so
get my laser pointer up. Okay, very
perfect.
good. Well, I'll just then wait. So you'll introduce me then, or tell me when to start?
Yes, it's 3:44. We're supposed to resume at 3:45 here. So yeah, let's just wait a few seconds in case that people are still
I'll wait for you
grabbing their
to
coffee.
cue me to start.
Thank you. All right. So thanks again, once again, Christopher, for your patience and for accepting this invitation. I would just like to briefly introduce you. So you are joining us from the NIST, which is the National Institute of Standards and Technology in the US. And we are really honored to have you here as one of the speakers of the MetCCUS seminar. Without further ado, I let you also complement the introduction, and I give the floor to you for the presentation on dew point measurements. Thank you.
Very nice. Thank you so much for the introduction, and it's a pleasure to be here. And thank you very much for the invitation to give my presentation here. So let me quickly introduce myself. I am working at the National Institute of Standards and Technology, or NIST, and I've been there now for about 34 years. And I do the humidity standards over there. I do both the research into humidity and also the hygrometer calibrations. Hygrometers, of course, are the instruments that measure humidity. And so we have nice facilities for humidity, both in terms of generators and hygrometers. And so I've been able to use some of those to make measurements of important thermophysical properties that are of use to industry. And in this case, they are of interest to the carbon capture, utilization, and storage. So let me also give credit to my theoretical colleague, Alan Harvey, who also works at NIST over in Boulder, Colorado. I work in the Gaithersburg facility, and he works in Applied Chemicals and Materials Division. The work that I'm going to be talking about, in case you don't understand it completely, it's been published already. This is work that was actually published about 8 years ago in the AICHE journal, that is the American Institute for Chemical Engineering journal. And the reference you can see below, and you'll be able to actually get this copy of the slides later on so that you can look up the paper if you're interested. Right, this I don't need to talk about too much because you know about this already, what carbon capture, utilization, and storage is. But what's important to know here is that you're having the flue gases coming from the power plants, and it's the CO2 then needs to be separated from the other flue gases. And in particular, it needs to be separated from the water vapor because a huge amount of the flue gases coming from a power plant is water vapor. And so that needs to be separated from the CO2. And then, of course, afterwards, the CO2 then can be utilized or it can be stored in different areas, which are mentioned down here. But anyway, so it's very important to remove the water vapor from humid CO2. And why? Because moisture in the CO2 can rust the steel pipes that it's going through. Another reason is that compression of the moist CO2 requires more energy. And certainly that's going to cost a lot more money than when you're doing compression that requires more energy. So designing a CO2 capture system requires accurate knowledge of the dew point in CO2 as a function of the mole fraction and the pressure. And so accurate knowledge then of this dew point temperature, which is here TDP, you'll be seeing this a lot in my talk, and as a function of the mole fraction or amount fraction X and the pressure, it can save a lot of money in the CCUS process. So how do you do that, determining the CO2 dew point relations? First of all, this is a very important equation here that relates the dew point to the water mole fraction. Here's the water mole fraction right here, and this is the dew point. And so let me explain to you what some of these other variables are in this very important equation. Along with the water mole fraction and the dew point, we have here, this is the saturated water vapor pressure at the dew point, which is gas independent. It doesn't matter what the carrier gas is. Then there's the pressure, and then there is the water vapor enhancement factor. So some of you may not know what E and F are, so let me quickly explain those to you. The saturated water vapor pressure is the vapor pressure above the liquid water that's going to be existing, and it's always going to be essentially the same at saturation. So for example, if you put some liquid water in a container and pump out all of the vapor that's inside of it and close off and valve off the container, then what's going to happen? The water is going to be evaporating until the vapor pressure reaches a certain value, and that's the saturated water vapor pressure. And if you then pump that vapor out again and close the valve off, the water will continue to evaporate until it reaches up to the saturated water vapor pressure, at which point then the evaporation will stop, or at least the evaporation will be in equilibrium with condensation. So that's the saturated water vapor pressure. Now this, I'm sure most of you are not familiar with, the water vapor enhancement factor. This is basically shows how much the saturated water vapor pressure is going to be enhanced or increased when you have a carrier gas that's interacting with the water vapor. And so, for example, this will be the case if you have CO2 in that container along with the liquid water. And basically, it's a sign of the non-ideality of the gas. And so if you have a very low pressure so that you effectively have an ideal gas mixture, then the water vapor enhancement factor will be 1. However, as you increase the pressure and you end up getting some collisions between the CO2 and the water vapor, then that's going to be increasing the saturated water vapor pressure. And so the water vapor enhancement factor will be greater than 1. Anyway, to sum up, the saturated water vapor pressure in vacuum is known. It's a well-known function that's been measured many times. However, the value of F, this water vapor enhancement factor, that is gas carrier dependent, and that needs to be determined for each individual gas that is in a mixture with the water vapor. All right, so we have a facility at NIST for determining what the water vapor enhancement factor is. So it's comprised of 2 parts. There's a saturation system, essentially a humidity generator, for compressed CO2. So it will generate an unknown water mole fraction using at a known pressure and dew point temperature. And then the second facility is, or part of the facility is a gravimetric hygrometer, which is a very unusual type of hygrometer. You only will find these in certain standards laboratories, because while it will make the most accurate measurement of the humidity possible, it also is very onerous to use, very difficult and time-consuming to use. So it's not useful at all to have these out in the field for standard, for normal measurements of the humidity. But in a standards lab like NIST, where we want to make absolutely the most accurate measurements possible, we have those, and that's what we're using here in this facility. So anyway, here's this equation that I showed you a little bit earlier, and here's F, what we're trying to determine. And so the saturation system will tell us this right here. By knowing what the dew point temperature, we can determine what the saturated water vapor pressure in vacuum is. Then we'll know what the pressure is from a pressure measurement. That's all from the saturation system. And then with the gravimetric hygrometer, we'll be measuring the water mole fraction. Okay, so let's talk now about the saturation system. So it saturates the CO2 completely with water vapor. That is, it brings it up to as much water vapor in the CO2 as the CO2 can hold at that temperature and pressure. And it operates at pressures up to 7 megapascal. That's the limit basically of our saturator, because otherwise we have to worry about it exploding, because it cannot handle pressures much higher than that. One advantage of this system is it allows frequent changes of water in the saturator, and that's important because the CO2 can react with water to make carbonic acid, even though the process is slow, but we certainly don't want to have carbonic acid in our liquid water in the saturator. All right, so here's the design for the saturation system. So we start off with a cylinder of dry CO2, and then we have a pressure controller so that we can control what the pressure coming out is going to be. We have here a needle valve which will allow the flow of the CO2 to go through this system. So if this is closed, then we'll basically have no flow of CO2 going through, but we'll make sure that it's all at the controlled temperature given by the pressure controller. And so then the gas will be basically going through our saturation system here and then coming through the output. So what's in here? Basically, we have in our saturation system, it's in a temperature controlled bath, as you can see right here, which is very important because we need to know what the dew point is. We need to know what the temperature in the saturator is, as well as the pressure. And we also have to make sure that the gas that's coming through comes to the temperature of the saturator. So it goes first through a heat exchanger, just basically a coil of 1/4-inch tubes. So by the time it gets to the pre-saturator, it should be at the temperature of the temperature controlled bath. And so here's our pre-saturator, which I'll be describing shortly. Then it is connected then to the final saturator. The pre-saturator does most all of the saturating. The final saturator does just a little tweaking, but it's important, the most important one, because we have here the measurements of the temperature and the pressure, which will tell us then what the dew point is going to be. And so we don't want to have too much saturation going on here, because saturation is going to be meaning that you're going to have a lot of water evaporating in the saturator. And the evaporation is going to be a cooling process for the liquid, and that can cause temperature gradients. So the way we handle that to get the best of both worlds is to have a pre-saturator, which does 99% of the saturating. And this can have some big temperature gradients in it. That can afford to have that, but then it goes through the bath again. This also acts again as a heat exchanger, and then to the final saturator, there's hardly any saturating done in it. And so it's just a little tweaking, so there's going to be hardly any temperature gradients inside of here. And again, then we have an expansion valve so that when the gas is coming out, then it can come down to close to ambient pressures. So this can be as high as 7 megapascal in here, and then when it comes out, it's just slightly above ambient, enough just to give pressure head to go through our gravimetric hygrometer. All right, so here's the design for the saturator. It's basically a pool of water that's half filled with water, and then there are directing baffles so that the CO2 is going through channels. So for example, it will be coming in here and half of it will be going around here. Sorry, here's the gas inlet, half of it comes here, the other half goes through here, then it comes here. Again, they split up and eventually they make their way over to the gas outlet. And the reason for having this tortured path for the CO2 to go through is to make sure that it has the maximum exposure to the water vapor so that we can feel confident that it is completely saturated, or at least close to saturation, by the time it comes out. Certainly it will be close to saturation in the pre-saturator, and then with the final saturator, we'll have confidence it's completely saturated. And so the design for the pre-saturator and the final saturator are exactly the same. It's just that they play two different functions. The pre-saturator comes first, the final saturator comes second, and of course the final saturator then has measurements for the pressure and the temperature. Temperature is measured by a thermometer that goes into a thermometer well here, as you can see, and then here we have a connection for the pressure, which is over here. And so this is a schematic of the saturator. This is the real thing. It's made out of 316L stainless steel. And so here you can see the baffles. Here is the bottom piece of this saturator, and here's a drain for it to go out. This actually had a little tube protruding through at the time, and that has since been milled off. So there's no tube protruding anymore. All right, so that's the saturation system. Let's talk about the gravimetric hygrometer. So it provides a primary method for humidity measurement and giving the water amount fraction x sub w. And here's the equation for how we get that. So it's basically, here's the equation. This is the mass of the water vapor. M sub g is the mass of the carrier gas. Capital M sub W is the molecular weight of the water vapor, and capital M sub G is the molecular weight of the carrier gas. So anyway, how do we then make the measurement? We first separate the moisture from the dry gas using desiccants. And once we do that, then we'll be determining the mass of the water by measuring the increase in mass of water in the water collection tubes. And I'll be showing you what these water collection tubes are in the next slide. Then after that, we'll determine what the mass of the gas is using volume, temperature, and pressure measurements and using the equation of state. And using this system, we can get relative uncertainty of about 0.1%, which is about as good as you can do with a humidity measurement these days. Here's the water collection tubes. They're basically, the core is the desiccant. In there we use magnesium perchlorate, and we make sure that it doesn't pass with the gas by using some quartz wool and also a filter sheet. Here's a stopper that we have for the gas to pass through, and that also makes sure that the desiccant doesn't spill out of the water collection tubes. And then finally, we have these caps here that are sealed with O-rings. So one really nice advantage of these water collection tubes is that we can put the caps on to seal them while it's in situ inside of the manifold. That's very important for this system because otherwise we could have ambient moisture getting into the water collection tubes. And we don't want that to happen at all. And so we make sure that we have a dry system, then we seal it up. At that point, then we can unseal the tubes and make sure that the only moisture that gets caught into the water collection tubes is moisture from the gas that we're passing through it. All right, then we make mass measurements of the water collection tubes before and after the water collection using an electronic balance that compares the mass to a standard mass. And it's a rather complicated procedure because you have to make sure that changes in the ambient pressure don't affect this mass measurement. I won't go into all of that because I simply don't have time in this talk. But this is the basic concept of the water collection tubes, that it measures the mass before and after. That's all due to the water collection in the tubes. And we use 3 tubes in series with each other for the water collection system. So most all of it is collected in the first tube. We'll have maybe a small amount, maybe about 2% collected in the second tube. And then the third tube is used really just to verify that we've collected all of the water. All right, so now let me mention the prover tube gas collection system. So basically we're passing the CO2 gas through these 2 prover tubes one at a time. And so when one of them is rising, the other one is, say, at the bottom. And so the valve then here is open, and then the gas, as the gas is flowing through, it will be raising the prover piston from the bottom until it reaches a certain level, at which time we'll close off the valve and then immediately open the valve to this one, and then the gas will be going through the second prover piston, so prover tube. And then while this piston is at the top, and while this one is rising, then we'll make a temperature and pressure measurement of the gas inside of this prover tube right here. And so, and then once those measurements have been made, then we'll open up a discharge valve, and then this prover piston can sink down to the bottom. And this all happens rather quickly. And so this prover piston will be down at the bottom here before this piston has actually made its way up to the top by going up through flow of the gas through the system. Anyway, hopefully that's reasonably clear. So with the measurements that we make of the temperature and pressure of inside of each of these prover tubes here, and knowing the displacement of the prover piston to give the volume measurement, then we can tell what basically the pressure, what the density is from the pressure and temperature measurements in the equation of state, and then from the volume that will give us the total mass of the gas that's inside of the prover piston. And so when we've finished with our water collection and finished a run that we've done, and we typically collect 2 grams of water inside of the water collection tube. And when we reach that point, then we simply stop the flow of gas through the system, and then we'll basically add up all of the masses in the gas collection system through each of the times that the piston has been going up through each cycle. And so that will then give us the water mass and the gas mass. And anyway, so just finally finishing up on the gas collection system, we use a laser interferometer system to measure the piston displacement to determine what the gas volume is. Again, we make the pressure and temperature measurements to determine the gas density once the prover piston has reached the top. We then have the gas mass under the piston calculated from the volume and density. All right, hopefully that's all pretty clear then. Okay, so here's our measurement plan. We made 6 measurements on 6 isotherms between 10 degrees C and 80 degrees C, and in pressure between 0.5 megapascal and 5 megapascal and 5.5 megapascal increments. The pressure range was limited by the CO2 saturated water vapor, saturated vapor pressure at ambient temperature, so we couldn't go above 5 megapascal, or else we'd reach the CO2 vapor pressure. Then we had to worry about CO2 hydrates, which can happen at high pressures and high pressures at low temperatures. All right, so here's the results we got. Water vapor enhancement factor, you can see it varied from 1 to 2. And these are actually pretty high values for water vapor enhancement factors, considerably higher than you'll find when the carrier gas is air. But anyway, you can see that here at the lowest temperature, you ended up getting the highest water vapor enhancement factors. And then, of course, as the pressure went up, then the value of the water vapor enhancement factor went up as well. So it increases monotonically with pressure, decreases monotonically with temperature. It varies from 1 to 2, and the difference, of course, say between 1 and 2 corresponds to a dew point change of 9.5 degrees C. So that's a pretty large amount. All right. We made some comparisons with theoretical results from Wheatley and Harvey. And so they provided through theory the value of the of B12, which is the second cross-virial coefficient. Now let me explain to you what that all is. So here you may be familiar with the virial equation of state right here, and here's the second virial coefficient B. But when you have a mixture of a carrier gas and water vapor, then you can separate B into this right here. This will be, B will be equal to the water mole fraction for, say, CO2 times B11. That's going to be the second virial coefficient for pure CO2. This is going to be the second virial coefficient for pure water vapor. And B12 is going to be the cross-virial coefficient between CO2 and water. So anyway, yeah, hopefully that's reasonably clear. Oh, and what we found here, when we used simply that value of B and didn't go beyond the second virial coefficient, as we assigned C to be 0, this is what we found here for the residuals. And you can see that as we got up to the higher pressures, the residuals increased considerably. So a conclusion for that was that we had to use a third virial coefficient. So what we ended up doing was doing best fit values to C122 and then the theoretical values of C122 being used. We tried using both of those. And anyway, here you can see what you have to do if you want to use the third virial coefficient as well as the second. And so we ended up using the best fit values for both C112 and B12. And in this case, our theoretical results, the residuals comparing with the theoretical results, were very nice. So here you can see that the residuals are really just scattered about 0, not totally randomly, but in pretty good results here. And so what we ended up doing then is using those values of best fit values of B12, which we then plotted here again as a function of temperature. These are the red values here, along with their uncertainty values. The uncertainties coming from the uncertainty of the fit, and compared them with the theoretical values and previous experimental values that had been done for B12. And so again, the line is the theoretical value from Wheatley and Harvey. This whole shaded area is the uncertainty from Wheatley and Harvey. And once again, these other ones are experimental measurements that were done earlier using some other means. And in a nutshell, looking at these results are our experimental results for B12, which is basically going to be what determines what the water vapor enhancement factor is. That agrees really well with the theoretical values. In fact, much better than the uncertainty of the theoretical values would indicate. But the bottom line is that they are in very good agreement to within the uncertainties. And so here's a tabular value of the theoretical values and our experimental values. And so in conclusion, as you all know, carbon capture, utilization, and storage has the potential of greatly reducing emissions of CO2 from power plants into the atmosphere. Water vapor enhancement factor is very important it's an important thermophysical property that you need if you want to do CCUS successfully, because you need to know what the dew point is as a function of the water mole fraction, so that you don't have too much rusting in the pipes for the CO2 and have too much compression, too much energy for the compression of the CO2. We've constructed a facility for measuring the water vapor enhancement factor, and it uses a humidity generator that saturates CO2 up to 5 megapascal, and we made measurements on 6 isotherms, and the measurements are in great agreement with the theoretical predictions. With that, I'll close and open it for questions.
Thank you, Christopher, for the presentation. It was perfect timing. Are there any questions in the audience? David Graham, please go ahead.
Yes, I'm just wondering if impurities make any difference. If the CO2 is above 95%, is it going to, anything else that's in the mix going to change dew points very much?
Yes, that certainly is going to be a possibility. It probably won't be changing the water vapor enhancement factor very significantly, but it can depend on what that impurity is. But certainly, and of course, it's going to be a hairy problem on a theoretical level, because it's hard enough to make calculations of the second cross-virial coefficient, even when you just have 2 gases involved. But if you have a multitude of gases, then it's going to get really hairy very quickly. But I would say, as an approximation, it's going to be, for as long as you don't have too many impurities there, I think that that the water vapor enhancement factor that we've calculated is going to do a very good job.
Is there a mixing rule for the enhancement factor when you've got other components present? So if you determine it for pure components, can you then combine them?
I don't think so. No, it's a very complicated situation theoretically when you have a multitude of gases, and probably the best way to address it would be experimentally. And so, for example, if you are having a gas that's a carrier gas that's 90% CO2 and 10% some other gas, the best thing to do would be make measurements using that gas combination for the carrier gas. So yeah, there are a lot more measurements that this system could be doing that would be useful.
Are you planning on doing more? This is at the very least
a good start. I'm sorry?
Are you planning on doing more measurements with different mixtures?
Yes. Yeah. Right now we're not. We don't have any immediate plans for doing CO2 along with another carrier gas. But again, it's largely going to be on demand. If the people in the industry who are interested in this need to contact us and let us know in some way that you need to have these kind of measurements done, and that will give us the motivation to do it, the knowledge that those measurements are necessary. And the other constraint, of course, is time. We are a bit cash and time constrained there. And I'll say, to be honest, being able to get some financial support for making these measurements would be very helpful.
Thank you, David, for the question, and Christopher for answering. Again, thank you for accepting the invitation. It was a pleasure to have you here in this seminar of the MetCCUS project. And I suggest that we move on to the last presentation that we have for the day. And for that, I introduce Karina Rinius, who works for RISE, and she will talk to us about the sampling of CO2 for purity assessment, which are the methods and challenges. The floor is yours, Karine.
Thank you, Miguel. Can you hear me well?
Yes.
And can you see my presentation?
Yes, we can see it.
Okay, thank you. I would like to talk about the sampling of CO2 for purity assessment and focus on the method that we can use and which challenges they have. So in this presentation, I will have first a short introduction, then we will talk about the challenges. We will discuss different vessels that can be used and different consideration that must be taken into account. And finally, we will talk more about material compatibility. And I listened to Martin's presentation, and there are some things that she has already mentioned, so it will be some repetitions. So due to the production method or the origin of the carbon dioxide, it usually contains species in trace that can have a negative impact on the equipment. So several standards contain specification for the CO2, and the specifications are different for the different applications. These standards often require analysis in laboratory, and this means that a sample needs to be collected and transported from the point of use. This sample must be representative of the gas supply. This implies that there is no compound added or removed during the sampling and transportation to the laboratory. So the challenges when we talk about species at trace level is mostly the risk of losing contaminant in the vessel or in the sampling line. It could be through partial or irreversible adsorption, or it could be by reaction between species or with the matrix. There is another challenge that we will not develop here. It's the need for flow measurement in some of the method. For example, when you sample on sorbent tube, if the exact composition is not known usually at the time you take the sample, and it could affect the value of the flow. So to sample, you have different vessels, and we can categorize them in two types. The one which produce no enrichment. This is the case when you sample in gas cylinder, in canister, or in sampling bags, and methods which produce an enrichment, like integer or sorbents. There are different considerations you must have in mind when you will take a sample. First, the condition at the sampling point must fit the requirement for the vessel. So for example, if the pressure at the sampling point is low, less than 1 bar, it will be difficult to fill a cylinder. And if the pressure is high, you will need to reduce the pressure for some of the vessels. We also need to think about temperature. For example, bags, sorbents have maximal operating temperature range. As I mentioned before, flow need to be controlled for some vessels and sometimes limited. And there is another aspect which is mostly for bags, is the risk of impurity coming through the bag through permeability. Another important aspect is that the requirement for the vessel must also fit the condition of the analytical instrument. That means that you need to sample an volume of gas that will be enough to perform all the analysis and all the replicates. You need to have enough pressure for some instrument, and for other instrument you may need to reduce the pressure. And also the same things apply with temperature. Many instruments work at ambient temperature. A very important aspect of the sampling is the material compatibility of the vessel. So the material in contact with gases that contain reactive impurity should be impermeable to all species and should have a minimum of sorption and chemical inertness to this constituent. The same consideration apply, of course, to all the part of the sampling line, especially where you have pressure reduction. Material compatibility issues are not often well demonstrated experimentally, and it is very important to increase the knowledge of adsorption effect of species on different material using relevant conditions, mostly pressure, temperature, concentration, matrix. So because of this, there is a need to perform systematic recovery experiment and short-term stability at relevant condition. And the result of this investigation can be then compiled in material compatibility tables to assist industry in selecting the suitable material for the vessels and the sampling line. So we at RISE, we are working closely with Swedish biomethane plants, which want to use the CO2 streams for different applications, such as producing gaseous beverage. And the pressure of this sampling point in these plants are usually only some millibars. So we think that sampling in bag is the best alternative for us. So in order to select the best option for the bags, we performed stability studies, and I will show you the result of some of the studies that we have been doing in the MetCCUS project so far. So we have selected 4 different bags. A bag called True Blue, which is produced by Airborne Labs and has been designed specifically for CO2 sampling. We don't have so much information on the material. It's a proprietary multi-layer biofilm. We have selected Cali 5 bonds from Calibrated Instrument Inc., which is multi-layer foil sampling bag that we have been using before in our laboratories. And we selected also a multi-foil from Restec, the same type of bag. And finally, Altef bags from Restec, which is made of PFDF film and known to be an alternative to Tedlar. So we have tested on different impurity. And here you can see the result that we have obtained for methanol in CO2 at around 7 ppm. You can see that in only one bag, methanol was stable for a long period, and in all the other bags, the concentration decreased quite fast, actually. So for this particular case, this bag were found to be the best alternative. These are the results that we have for acetaldehyde. Here you can see that all the bags give good stability. However, we perform our test at quite high concentration, 7 and 13 ppm, when the limit required in, for example, IGA document is 0.2. This is the result for ethanol, where we observe a much better stability than for methanol, but still some decrease is observed with time. The best bag is the True Blue in this case. Here we have the result for acetone, for which we have 2 bags in which the stability was good, in the true blue and in the Cali 5 bond. We show a small decrease in ALTEF bags. These are the results for benzene. Here again, we worked at too high concentration, but the results were stable. However, in the multi-layer foil, we observe loss of benzene directly at the first day. So this bag is not appropriate for benzene. And these are the results that we have for H2S at different concentration in a Cali 5 bond. And you can see that the stability was good at all concentration. But for this test, we used an OFCEAS instrument, which allows us to measure oxygen and water at the same time. And we could see that oxygen did not come into the bag with time, not so much. We started with around 200 ppm in the bag, and after 9 days, we had only 300 ppm, so not such a big increase. But you can see that this bag have a very high permeability for water. So at the beginning of the test, we had only 400 ppm of water in the bag. And after only 3 hours, we were at 2,500 ppm, and it goes up until 9,000 ppm. So to summarize the test that we have, you can see that we didn't find one bag that will be good for all the impurity. Sorry, the best results were obtained with true blue, but methanol was not stable in this one. We believe that we could also have good result in Restec multifoil, for which methanol is stable. It was the only bag that gives good stability for methanol, but it can't be used for benzene because we lost it directly. So we would like to continue the test, and for example, we could try to see the stability of hydrogen sulfide in true blue and in Restec. We want to work with acetaldehyde and benzene at much lower concentration, and we would like to confirm that ethanol and acetone will be stable in Restec multilayer. So the conclusion that we have from this study is that no single bag is suitable for sampling of all the impurity that can be present in CO2. It is likely that we need to combine several vessels to cover the wide range of urine impurity. The best results were obtained for true blue, which has been specifically developed to sample CO2, but it didn't work so well for methanol. And we think that a good candidate could also be Restec multilayer. This result also highlights the need to perform stability studies in relevant conditions. There are other studies that are interesting. It's to combine several impurities to see if you can see any influence, but this is not planned in this project. So that was all. Thank you for your attention. I don't know if you have any question.
Thank you, Karin. Yes, there is already a question in the chat. Someone is asking why you chose to test bags and not gas cylinders, for example.
Because of the pressure. The place where we take the samples for our stakeholder is biogas plants, and the pressure is very low at the sampling point. It's only some millibars, so it will require to compress the gas if you want to take in cylinders, and you can introduce impurity by doing this. So bags in that case are a much better alternative.
Okay, thanks, Karin. Same question, would inerted canisters be better? One container type would be very beneficial. That's a comment from Dave. It's more a comment, I would say. And what about cross-contaminants effect? Do you see a worse performance in case of real samples where different components are present at the same time?
Yeah, we believe that this could. Some tests have been done in another project in Metrologica 2, and here they could see that there is some influence when you have several compounds together, but it's quite limited. It's not so many, but it's of course very important to study.
Mm-hmm. And finally, I see another question regarding next steps. Will you publish an article concerning your tests soon?
Yes, probably. At least it will be a report. We will see. We have an article that we need to write, but we don't know if we will include this test or other tests we have been doing on sorbents, for example.
Okay, thanks, Karin. I also put in the chat a couple of reports that you have already produced, which are mostly literature surveys on the current state of the art for material compatibility and the available cylinders for the preparation of PRMs. Yeah, thank you for the presentation, Karin. One comment. And do you use bugs once? That's the last question that we have in the chat.
Do I use what?
Bugs once. I don't know if you want to clarify, Alexander, to give more details about your question.
Yeah, it's very simple. Do you use only one new bag for one sampling, or do you reuse bags?
No.
Okay.
We don't reuse bags. We use them once.
All right. Thanks, Karin, for the presentation. It was really interesting, and you addressed all the questions, so that's perfect.
Thank you, Miguel.
In that case, this was the last formal presentation that we had prepared for today, and we can move on to the closing remarks. And for that, I give the floor back to Iris, the project coordinator of MetCCUS, who is going to say a few words to finalize the meeting and thank everybody.
Yes, thank you, Miguel. Let me share my screen. I prepared a short presentation. I hope you can see my screen now.
Yes.
Oh, perfect. As I said this morning, during the day, I wanted to see what kind of challenges came across during the presentations and also in discussion, and also during the survey that we sent out. We got many measurement challenges and challenges for CCUS sent back to us. So I just want to give a short summary of those. I first want to start with participants. So at the beginning of the day, Miguel sent out this poll to ask several questions. One of them was where you come from, which country you are in, and as you can see, we have quite a diverse group of participants from many different countries. There are quite some from the Netherlands, but yeah, we're coordinating this project from the Netherlands, so that might help to have a few more people from the Netherlands in here as well. And even a few people from outside of Europe, so Iraq, and we just had a presentation from someone from the VS. So that's very good. I think really good to see that CCUS is important in many different places in the world. So then the CCUS challenges I came across. There are many general challenges, which I just summed up here. In the next slide, I will look at really the measurement challenges. But many of them were mentioned. So organization of ring tests, I think this is a very important one. So in the MetCCUS project, we will set up measurement methods, calibration methods, and also reference materials. And once those are available, also ring test or interlaboratory comparisons or proficiency test can be set up. So that's something that I think people in the MetCCUS or partners in the MetCCUS project are working on, but maybe these tests are also available by other parties. Then direct air capture was mentioned, something that has not really been addressed in the MetCCUS project, but I think becomes more and more important. So that is something to keep in mind for the future. Tracing the origin of CO2 becomes more and more important as well, especially for biofuels. And when you utilize the CO2, you need to make sure that you know where your CO2 is coming from. Also, this is not addressed in the MetCCUS project, but really something to consider for future research. Standardization is also mentioned a lot today. As said, there is an ISO group working on standardization for CCUS. Currently, they're setting up a STEN group to develop standards and documentary standards for CCUS. As the MetCCUS consortium, we provide input into those standardization committees, and in that way try to help set up these very important documentary standards, which will definitely help the industry to be able to perform measurements, but also for carbon accounting and many other aspects that are important in CCUS. Other things that came up are unclear specifications for CO2 and impurities. Of course, it is an upcoming field, so I think there is still work to be done to make those specifications more clear and to maybe also just write those specifications. Diversity of applications along the CCUS value chain. As mentioned, you can apply the CCUS process to each industry that you can find, and that makes this diversity, of course, very large, but it also makes it more difficult to write specifications for CCUS and for CO2. There were some challenges regarding storage. How can you arrange the storage? How can you arrange storage between different countries? Yeah, there are things to be figured out too. And as mentioned in one of the presentations, the Portos project, it will open, I guess, in 2026. And then from there on, slowly we will learn much more about storage of CO2. So slowly these type of projects start to be open and really start to store CO2. Another one is legislation and carbon accounting, which are of course very important and will become more and more important in the future, and where work still needs to be done, as I already said before. A few others are how much carbon do we need to capture to become carbon neutral? How much captured carbon can we convert to fuels, chemicals, and other materials? And yeah, as I think I already mentioned that in storage, how can we connect different CO2 networks? So those are a few challenges I picked up today. Maybe I forgot many, but so if you have any that I forgot, just write them in the chat if you think they are important and should be in this list as well. Just let me know. So these were general challenges, and now I'm trying to go to the measurement challenges that I came across. So I put them in the 4 categories that the MetCCUS project is working on. So flow metering, emission monitoring, and on the next slide, I have chemical metrology and physical properties. But let's start with flow metering. I think the most important challenge there was ensuring accuracy and measurements across a wide flow range of CO2, and also with variable CO2 purity, because as we hear today, the CO2 is not always 100% pure. It will contain impurities that, from different industries. So the other one is calibrated, accredited, and accurate flow measurements for supercritical CO2 flow with acceptable uncertainties. Especially the supercritical CO2 flow measurements came back several times, so that's also a very important one. Measuring for allocation, flow meters suitable for physical flow measurements and traceable to the international standards. I think we've heard some options today, but still traceability to the international standards is something that we're developing in the MetCCUS project. And transferability of alternative fluid calibrations. So for example, with water compared to liquid CO2. We also saw some results for that, but I think more research is needed there as well. Emission monitoring. Amines breakthrough and products emissions are very important there. SO3 emissions, which has been discussed a lot today as well. Amines and flue gas and number of species and concentration levels. Pipeline leak detection and direct measurements of CO2, preferably post-capture. So those are things to really look into emission monitoring, and many of these aspects are also addressed in the MetCCUS project. Then the last two, chemical metrology and physical properties, starting with chemical metrology. So there's a request for CO2 traceable standards and reference gas mixtures. Compounds which really stood out were amines, NOx and SOx, metals such as mercury and candela, I think, cadmium, sorry, at different levels. So the amines and NOx, SOx at ppm level, the metals at ppb level, and also dust was discussed today. Of course, next to the reference materials, also analytical methods are very important for online measurements of impurities. And need of sampling protocols. So the last presentation was all about sampling, but not also looking at materials, but also looking at pressure, temperature, flow rate, and gas composition, and to make sure that we have compatible materials for that. And we are doing more research on this in the MetCCUS project as well. And the analysis of the raw gas, so not only the very pure CO2, which is sent into storage, but also the CO2, which has just been captured. Then the last one, physical properties. Need for data to verify models to predict the physical properties of CO2. So that's something we are working on in the MetCCUS project as well. Thermodynamic state and gas properties after capture. Emission equations of state, and something that has been mentioned is how will these be implemented in flow computers for physical metering, and accurate measurements and analysis of moisture in CO2. I put this with physical properties, as in the MetCCUS project, the measurement of moisture in CO2 falls under physical properties. So those are the challenges that I picked up during the day, and I think there are many. Some of them are addressed in the MetCCUS project. Others are still open, and I think can be addressed in future projects or in other via other pathways. But there is still a lot of work to be done. But I think also with the seminar today, we set a first step in, or again, another step, I should say, in addressing these challenges and seeing how we can go forward from this on. So from my side, I want to thank the speakers today who gave a presentation. Really, thank you for taking the time to contribute to our seminar, for the participants, and also for the very good discussions that we had, mainly in the chat, because there were over 80 people constantly in the seminar. So that's a lot of people to really have a good discussions online. But I think that we made a good step with the discussions in the chat. And I'm looking forward to meet you all during other events that the CCUS project is going to set up. If you're interested to follow us, you can visit our website or follow us on LinkedIn, and there you can find the latest information that we or research outputs or reports, but also events that we're organizing in the future. So that was it from my side, and I would like to give the word back to Miguel, and also thank him for the good organization together with Eleni of this seminar. So thank you for your attention.
Thank you very much, Iris, for being here all the time as well, all your efforts coordinating the project. Just no more to say. Thank you, the speakers. Thank you, the participants. And this event, I think, was really successful, and I hope that all of you have enjoyed this. Thank you for joining from all around the world. It was a pleasure. and enjoy the rest of the afternoon. You have 13 minutes before the final closure, so have a nice afternoon.
Thank you. Thank you.
Goodbye, everyone. Thanks.
Goodbye.
Thank you. Bye.
Goodbye.
Goodbye.
Bye.